finish it soon. See, this takes hours to boot in. Hello. I have to inform these guys to open this bit early. Like, well, I don't know why they wait until. See, we can't start.
Ticking is not consistent every week as well. It's an automatic timer that's not consistent week to week.
Yeah. So they just change it, 10 minutes, at least 10 minutes.
It's just messing with you. Yeah.
I have to. This class, I have to inform them. I'll just start using my finally. Do you guys also have this, triple or double authentication thing now?
I don't get it on my drive, but on my staff one, not on my student. Yeah, the ringing calls students.
If I forget this one, then I'll be in big trouble. Whole day I can't do anything.
It's all right on your own computer because you log in once a week, so that's only once a week.
Yeah, but still sometimes that it's, even though you said it once a week.
Yeah. Well, I mean, coming on the computer, on the computers, yeah, it's when you ask every time.
Yeah.
Yeah, I figure my student one will be the last one to put on to that. My student number's got the oldest here. my number's older than Matt DeSouza's and Chapman's, etc.
Okay, finally. Oh my goodness, very sharp. Yeah, it's there. Not that I. Okay, Thomas, can you hear me? Thanks. Sorry for the delay. I'm trying to. Slide. trying to fix Zoom and oops. Okay, good morning. Yeah, we are almost at the middle of the semester. And as I said, we will have a couple of industry lecturers in coming weeks, and then please attend those sessions. The material they cover sometimes will be useful for your exams, as well as it's good to have that interaction with the industries. So at the end of the day, that you will go and then work for them. So this week that I'm going to talk about another protection scheme, and then I will quickly move into the instrument transformer section, right? So I have uploaded the notes yesterday. So I will go through those instrument transformers, and then we will do some calculations related to them on Friday. And then next week we will start hardware labs. I will upload those sort of instruction sheets for those labs this way. And then you may have to get some understanding or some background information about it when you write the report, like sort of what you have experienced in the lab. It's a part of that report. So please attend those labs as well. And then for online students or the external students, we will upload some videos so that you can get some sort of experience, not the 100% as attending the lab, but still you will see something what we are doing in the lab. Okay. And also the tutorial submission is due next week, Monday. So if you have any questions related to that, just start to work on those questions, and then we can discuss those things, right? And then this is a part of your learning curve, so you can, if you know how to solve those problems, then it might be easier in the exams as well. Okay, so far that we discussed about different mechanisms to identify fault currents, and then another technique is called a differential protection scheme, which is also sort of identifying the fault currents. So in the previous two techniques that we usually identified those, let's say, when the current magnitudes are high, or let's say compared to the load current, when the current magnitudes are high, then you can identify those things by looking at the current magnitudes or impedance of the system in front of you. Impedance is low means that there should be some problem. Impedance low means that there should be a high current in the system. But there are cases where when you go into examples like, let's say, generators, transformers, sort of motors, those sort of specific devices, sometimes what happens is that there might be some insulation, let's say, break, rather than insulation failure. I would say that if the insulation is not 100% doing its purpose, so it's sort of aging, then what happens is that sometimes it started to have sort of high current passing through the insulation systems. Let's say it could be some milliamps or let's say a couple of amps, which is not good for the overall operation of the system. Because now what happens is that, say through the insulation, if the current starts to leak, then the insulation temperature will go up, and then sort of the damage will be non-recoverable. So what we need to do is that we need to identify at a stage when the current magnitudes are smaller, so that you can take some precautions. Now, the techniques that we described before, they are not capable of identifying that sort of small currents, because they are not, sometimes they are not, they are basically comparable to load currents. So there's no way to identify it. So for these devices, when we want to look at these sort of small currents, for these sort of, let's say, generator or transformer or some sort of protected equipment, what we do, we simply measure input current and output current. Okay, so you have two wires, one coming in and the other side probably going out, right? As an example, in a generator, one side is connected to the neutral, the other side is probably connected to the phase. And then why not, like, you measure the phases and the neutral. So if it is Y connected, then the addition of the three phases should be equal to what? Neutral. If it is not, then, which means that in between those two, there should be some sort of a current leakage. So very easy to do that. So you call that sort of protection scheme as differential protection scheme. So mainly they are used for these sort of electrical equipments, and you compare the input and output currents. So one of the important things here is that when you compare those two currents, now to measure that current, you can't just measure it like you can't just put an ammeter somewhere here. Your measuring circuit should be isolated from the power circuit. So that's why that you need to put a current transformer here and another current transformer in the other side, and then you measure that current in the secondary circuit. So that this is the primary circuit, is the one which the equipment is connected. The secondary circuit is the circuit where the CT secondaries are connected. So you can see that there are some dots here. The reason is that when you connect a transformer, right, if you connect in a, let's say, reverse direction, then there is a 180 degrees phase shift of the current. So we want always to connect them, both of these CTs, in a way that addition of these currents will give you the 0, right? So that basically I1 and I2 are equal, which means I1 minus I2 is equal to 0 if there is no fault. So that if there is a fault, you can see that there is a current I1 minus I2 flows between these two. Otherwise, this I1 goes through this secondary, is equal to I2 coming back to this CT, so that the both currents will be equal. But so it's quite simple technique, but when you implement it, you need to consider a couple of factors, like, as an example, turns ratios of the CTs and then direction of these windings. So those are quite important parameters to be considered, right? So what we do in this sort of arrangement, we will look at the magnitude of this leakage current, right? Usually 0 is not a good number. You don't say that, if the current is above 0, it should be operated. We don't do that, right? Because always there might be some cases where the noise current is going through it, or some small leakages in the equipment, or probably capacitive leakages, right? So because of them, this I1 minus I2 is not always 0. So that you set it to a small value, let's say 0.1 amps. Above 0.1 amps, it will operate. So that setting is called as pickup value. So if the differential current is above the pickup value, it will send the signal to the relay. I thought my phone is off. Okay. Done. So it is quite easy to implement, as you can see here, for normal operation of fault outside the okay. So what happens is that now which zone is protected from this this sort of differential scheme, that is also important, right? Say if there is a fault, somewhere here, can you tell me what is the current difference between, say if the fault is somewhere here, right? What is the current difference between I1 minus I2? Just apply the KCL. Whether there is any difference between I1, like let's say in normal operation, let's say I1 and I minus I2 is 0, right? There's no fault in this system, and then I1 minus I2 is 0 because they are equal. Now if there is a fault here, what is the I1, the value of I1 minus I2? I don't know why it doesn't. Okay. It's the same, right? Still I1 minus I2 is 0. Why? Because you are outside the protected zone. So this technique, you can clearly define the boundaries which it identifies, right? So the boundary is from this CT to this CT. So that's what it is written as protected element. Can you see that? So that's in between that. If there is a fault, like as an example, if this fault is here, then there will be a current difference, because you can clearly see that certain part of the current is going to the ground, but then therefore I1 coming into this protected zone is not equal to I2, right? So fault current plus I2 will be equal to I1, something like that. So this is the beauty of it, because in the previous ones, that when you are considering the boundaries, you set something in the relay, right? Because you are looking at the impedance. And then the other important thing there is let's say the line conditions could change. And then the protection zone could move further up or can be shortened, because it depends on the line impedance, right, or line conditions. But then in this case, it is fixed. As long as you have physically connected something in between, then yes, that is the protection zone. So that is the one of the advantages of these differential schemes, that it's not affected by external factors like in the other two. Now, if you think about these differential relay schemes, extension of it is called as pilot relays. When we will discuss about that's basically when you have these transmission lines, you can put a differential protection for them, like at this beginning of the transmission line and end of the transmission line, you put a differential scheme, and then you can see whether there is any sort of fault in the transmission line. Then there will be a current difference, because the transmission line is you can define it as one unit. But then for differential protection schemes, you can see that both currents. Secondary current has to be measured as well. How practical it is to have, let's say, 200 kilometer transmission line that your secondary circuits should be connected, right? So you have to take the secondary current from the other end and then this end and then compare. Do you think that is practical? No.
Just don't need fiber optics.
Yeah.
You could send stuff there easily.
That's the, like, the, even without fiber optics, if you have microwave links, right? So that's how they do it. That's called pilot relays.
So if they'll have that one in and then they'll have this traditional
Impedance as well.
impedance as well. So if the thing that one fails and the other one cuts in, so you don't have to
Rely on one thing,
but
yeah.
You have that as a far better source.
Yes,
Time delay.
exactly. Yeah. And then when you are going with the real protection schemes that you don't rely on one technique, that's why that you have very reliable electricity. Like, you are looking at many different factors, right? So because each different schemes have their own advantages. And then when you combine their outcome, even you can locate the exact location of the fault. Like as an example, using this technique, you can't think of the exact location, right? You know that in between these two. But probably with the impedance relays, you can sometimes even think of whether it happened in the far end or this end. So you get different information from different schemes. And even the current magnitudes is still over current relays are used, right? So heaps of different ways, but this is also, but when you are looking at transformers or generators, then impedance relays doesn't work. And then overcurrent relays is not sometimes not sufficient. So that's why this is the differential relays are a must for unit protection. So if you have a certain unit, for them differential protection is a must. So if you are looking at any fault inside this zone, then you can see that there is a fault current IF, which is basically going through this center branch. And then the relay will only operate if that difference, the magnitude of it, is larger than the pickup value. And then if it is less than the pickup value, it blocks. So we are the one who set that IP. We say that IP is this value. That depends on a lot of other conditions, right? So the magnitudes of the currents that you are working with, and then what is the typical leakage current, right? A lot of other things will define this IP value. And one of the issues with this scheme is, let's say that the apparent power of this unit is, let's say, 1000 MVA, and then the load current is 100 amps, number one unit. There's number two unit, apparent power is, let's say, 100 MVA, load current is 10 amp. Okay. Unit 1, the load current is 100 amps, normal rated. Unit 2, normal rated conditions, 10 amp. Now, if I set my differential relay to operate when the current is 1 amp, right? I will tell that differential relay will operate when the current difference between these two phases is 1 amp. How feasible it is for these two systems? Let's say 400 amps, first step. Rated is 100. If the current difference is 1 amp, that is 1%, which is okay. What we say that, okay, 1%, right? Now look at the 10 amp one. If you set 1 amps as the operation current, then what is the percentage? 10%, right? Pick up 1 when the load current is 10, but my pickup current, which is the difference, what we are now looking at, is 10% of the load current. What do you think? Is it too high? 10%? Like, let's say what happens then when the current is 1% of the load current. Relay won't operate. Right? Got the point? Like, when the load current goes up, if you keep let's say, if you keep your pickup current level as a constant value, let's say 1 amp, and then if you change the load current, let's say when the load current is decreasing, let's say your rated current is coming closer and closer to the pickup current. So, which means that the system will not be able to identify the small faults. The purpose of having differential relay is we want to identify the initial faults. Like they won't create, let's say 10% of the load current at the initial stage. It could be 1%. It could be it could be 0.1%. Small low fault currents, right? But with this scheme, it is hard to identify if you just look at the absolute pickup values. Right? As an example, absolute pickup means you take a relay, you tell the relay to operate when let's say the differential current is 1 amp, which is the absolute value. Right? So then to overcome this issue, we are looking at something called the same scheme, but it operates in a different way. So the pickup is we identify the pickup in a different way. That is called percentage differential relay. What does that mean? You can see that the conditions here. Earlier, the current difference, right, was, let's say, larger than a certain given constant value, then it was tripped. But now, this pickup value is also changing with I1 and I2. Right? So that is the average of the two currents. See, K is a constant. You can set it 0.1 or 0.01, whatever. Right? But then the value depends on, the trip value depends on the current going in these lines. So now, when the current goes up, your pickup setting is increasing. When the current goes down, the pickup setting decreases. So now, always you are looking at a certain percentage of the total current going through the system. So that makes sense in a way that you are not, let's say, you are not operating it for unnecessary conditions, and also you can operate it for all the required conditions. So that's why percentage differential relay is the more practical one, right? And also that one of the reasons for this is the errors associated with the CTs, because all the CTs are not 100% correct, right? And then if you are going for a very small differential scheme values, then that may be introduced by the relay errors, the CT errors, not by the real fault, right? So to avoid all those issues, then we can go for this one, right? So always the pickup is not a constant, it changes with the load conditions. So that's because I'm not going into detail here, because you will, when the industry lecturer will talk about the transformer protection, then he will talk about this differential relay key. So that is the application side of it, okay? How that relay is used in that work, okay? And of course, generators, they'll be used, and when we talk about the pilot relays, I will come back to this, okay? So that the operation of it is very simple. No much maths is involved, okay? But there are a couple of differential schemes that I will talk about it even in bus bar protection, right? So when I come to these different specific protection schemes, we will use differential protection scheme in those ones, okay? Okay. So, any questions so far? This is recording, right? Yeah. The new topic that I'm going to start today is about instrument transformers. So instrument transformers is basically we already have discussed about them, like the application. They are the one that's they measure the voltage and current and then feed those values to relays. So therefore they play a big role in the protection schemes. And the purpose of having them is that you need to have safe level of measurements. And then you want to isolate the primary circuit and the secondary measuring circuit, right? Because primary circuits, they involve in, let's say, very, very high voltage levels, but our instruments, usually electronic instruments, they prefer lower voltage levels. The advantages of having them, you can say that to obtain input levels for relays and, as I said, associate hardware containing electronic components, right? Because electronic components, they need lower voltage levels, and then that's how we supply it. And the other through the ITs. And the other important thing is that for high voltage assets like transmission lines or power transformers or generators, usually the maintenance crew or the people don't usually go there and then do a lot of things. Then you have to take it out of operation, or you need to have some safety precautions for those work. But when you are looking at the, let's say, relay operation level, then people may, or maintenance crew or engineers, have to frequently visit those places and then do some measurements and all. And then these sort of lower voltage or lower power levels will give you the personal safety, right? So that's the reduce the risk. From the operation point of view, they are no difference from the normal transformers. You can say, if you know the purpose of a transformer, then that is the same thing here, right? So it can drop the voltages or it can drop the current magnitudes. That's what it does. And then when you are looking at the, let's say, recent developments, there are things without this transform operation, like Hall effect sensors and all. You can use them as CTs, right? There are ways to operate or to get the information without using the instrument transformers. Probably in, I don't know how many years, but in decades time, probably these things will not be used, right? You can use Hall effect sensors to measure the current and voltage. We are not reliable as them still, right? But then, it's like with time things change, right? So, yeah, if you think about optical fibers about how many, 20 years or 10 years back, it was very expensive, not 10, probably 20 years back. It was not that cheap. But now, you can put it even inside the house that you can put optical fibers, right? So that's what happens with the technology. So the power levels they involve is always very low. That is like, let's say VA levels, right? Not MVA or KVA levels, right? We are looking at very small power. So this is a typical power transformer. If you look at it, I think I've shown this picture in the previous, when we started the course as well. You can see that they have sort of two live connections. One is the current coming in and the other one is current going out. And then inside this, that you have the measuring techniques, right? So I will come into, there will be a couple of slides about how what sort of internal construction is there. And this side of this column is grounded, right? And then say in a CT, as we know, that what you need is that you need to have some sort of inside this, So inside this, basically this is the wire, this wire, and then some sort of a toroid is like that. So this is the connection that you have inside, right? The current is going through this sort of toroid, and then you have some extra, another secondary term turns or secondary winding around it, and then this will have certain current measurement. So this is the I primary, and this is the I secondary, right? And that secondary is fed to the relay. Then we have these all insulators and all, those are the extra protection for high voltages and things like that. But what you can see here in the left hand side, this is the basic operation of it, right? It's very simple. So there are many different applications when you are looking at the CTs, not only for the protection circuits. Basically, the purpose is, as I said, the CTs are used to measure the currents, right, in a system where you have large magnitude of currents. But then when you are looking at the applications on the power systems, then there are mainly two types of CTs that we use. One is for these protection circuits. Those are called protective CTs. The other one is not only that. If you go into a substation or if you go into a SCADA system, you will see that in this line 100 amps is going through, and then in this transformer, when the transformer is full load, now the current is this much. All those information is there. So that is called measuring CTs. So what you do is that you measure the currents going through the system. Okay, so that's the other type. So you have two types, measuring CTs and protective CTs, right? So out of them, which one needs very high accuracy? Measuring, because measuring is quite important. Like, you want to know whether the current is exactly at 1 amp or 100 amps, or is it 105 amps? Sometimes when the fault happens, it doesn't matter whether it is 105 amps or 108 amps. If it is overload, it's overload, right? So it's from the accuracy point of view, and the measuring CTs require very high accurate performance, but they don't need to perform well when there is a fault. You don't need to measure the fault current magnitude. What you need to know is that fault current is very high, right? So that their accuracy is important in this range, 10% to 120% of the rated primary currents. So that is basically real loading conditions. Under real loading conditions, you need to know exactly how much current is going through. And usually, when the load current is go beyond the 120%, then usually these measuring CTs, they go into their saturate, like every CT will saturate at one level. When the current magnitude is going into it, you can't have a CT which will never saturate, right? CTs will saturate at a certain level of current. But regarding the measuring CTs, since you are not interested of measuring the current, high magnitudes, then they usually go into saturation after 120%. That helps to protect the secondary circuits as well. Otherwise, what happens? Let's say your secondary circuit can measure up to 10 amps in the secondary circuit, but what happens if the CT, let's say during a fault, 10 amp corresponds to your full loading conditions. During a fault, that can go up to 100 amps. And then if you try to measure 100 amp in your secondary circuit in a measuring device, the measuring device will, what happens? That will basically collapse. So it depends on situation, like, it goes into the, so it will do erroneous measurements or the completely destroy, right, because of the high current magnitudes. To avoid that, what they do, when it is going beyond these regular current limits, the transformer, the CT is pushed into saturation region. Once it is saturated, secondary current is not weak. Even though the primary current is high, the secondary current maintains at a constant level. So that's why that this sort of saturation is also important. Yeah. So from the protective CTs, what happens if for a fault protective CT saturate? Do you allow the protective CTs to saturate? No. That's like they don't have to be accurate, but they shouldn't be saturated for a, let's say, even 10 times of the load current, right? Because the fault current might be very, very high. So that saturation point of view, protective CTs, they perform well, or they don't go into saturation, right? So those are the major two differences between them. If you are looking at the construction of these CTs, as I said before, it is very easy. From, let's say, operation point of view, it's a very simple construction. But when you are going into the practical implementation, then a lot of other things are there because of the high voltages, and then they say you need to look at their performance under different weather conditions, and their outdoor units, and then you need to think about cost, right? All those things. So when you combine all those things, then the construction is not very simple, right? So usually you have these sort of insulators, and then on top of that, inside this column, you will sometimes have oil to cool it down, a lot of other things, right? So from the construction point of view, there are a bit complex, but the operation point of view, it is simple. So you can see that wire, toroid, and then the secondary circuit. That's all. And another important thing with them is that this dot convention. Can you remember? What does dot convention means? Because it is very important for CTs, because if you are connecting two CTs, even especially for a differential application, then you need to remember what this dot means. The dot means that a current going into this dot in the primary circuit will produce a current coming out of that dot in the secondary. And then these two are in phase. These two are in phase. So if you mark the current going into the dot in one circuit, the current coming out of the other circuit, those two are in phase. So when you are doing the calculation, when you are connecting them, you have to think about it, right? So in which direction they are in phase. Yeah, so from the construction wise, the primary winding is only a single turn because just one wire. Secondary terminal will have multiple turns depending on the ratio that you want to maintain. And then this dot convention, which I mentioned here, it is valid for normal transformers or any winding, right? So it is the same convention. Current going into the dot, current coming out of the dot in the other winding, they are in phase. So if you look at this, you can have the dots in multiple ways like that. You can mark them, right? So in every connections here, you have a relationship between the secondary voltages and the primary voltages. And then also the secondary currents and the primary currents. So this is the relationship, whether you need to put a minus or not, depending on dot locations and the current and voltages you marked. So as you can see here, if you mark the current coming into the dot in one winding and then out of the dot of the other winding, relationship which is positive. Going to the second one, current going into the one, and then the other one also current is marked going into the dot. Then the relationship is the negative side because they are 180 degrees phase shift. Okay. And voltage, how do we mark voltage, which is not important for current transformers much, but then there is a way of doing it for the voltage as well. What does that mean? If you mark the polarity of the voltages, the positive to the dot direction, or if they are, let's say, the polarities are the same towards the dot, then the relationship is positive. Now look at this one. Polarities are not the same towards the dot, right? Towards the dot positive, towards the dot negative. Then the relationship is negative, right? Negative means 180 degrees phase shift, that's all. Which means that in one phase, when you mark it, this, or when you are looking at this current, if the one current is going up, the other one is going down. So 180, that's why you have this negative relationship. Remember that. This is not only for this, for any transformer or any inductor, right? That's what dot means. Got it? And then we can go into, when we are studying about the CTs, it is also important to look at sometimes the equivalent circuit for calculations. So transformer equivalent circuit is valid here, but the difference between the normal transformer and this equivalent circuit is, when we are doing the calculations, typically in a transformer you can remember that you apply a primary voltage VP, right? Now, are we applying a voltage to the primary or current? That is the main difference, right? Because it's a CT. In a CT, so that instead of a primary voltage here, you need to put a current source or current IP, right? In a calculation, a current IP is going through it. And then the rest of the circuit is the same as normal transformer equivalent circuit. You can see that the center branch is called the magnetization branch, and then this is the load branch where the RB and LB, these are the sort of the impedance coming from the relays, and then this part is coming from wires and also the transformers or the CT inductance, CT resistance. And then if you have a wire resistance, you can add them to here as well. Okay, so that this part, usually we represent all these things in the secondary side of the circuit, because primary side we keep it as just a current source supplying, like certain amount of current that is going through the primary winding. How another sort of silly question. If you are looking at this, what happens, let's say for the primary current for a CT, right? Let's say you have think about this from the power system point of view now. You have connected a CT to measure the current, and then let's say mistakenly something happened in the secondary circuit, and then you apply a, say, certain magnitude of current here or something, right? Like let's say apply the voltage source here. What happens to this primary current? Don't look at just the equivalent circuit, but think about the real power system as well. So you do something in the relay room, right? In the relay room, you do some things, like let's say mistakenly you connect these two across a battery, right? What happens to the current in the primary circuit? So you have a 100 MVA system where hundreds of amps going through the conductors. You have a CT, and then you do something mistake in the secondary circuit. Do you think that will change the amount of power going through transmission lines? 100 MVA? Nah, right? So it will affect the CT. CT could, probably, it go into saturation or whatever, different things could happen, right? But it won't affect the primary current, right? So this equivalent circuit is valid, but then at the same time, remember that their relationship is sort of from the primary side current, the secondary side currents and all can be derived. But if you go from the secondary side to the primary side, there's no meaning, right? Because you're not going to do anything on that 100 MVA transmission line by changing a small battery in the secondary side. The power is not enough there, right? So, okay. So these are the typical. We will do some calculations related to them in the tutorial, and then I have some in lectures as well. So what you need to understand is that these parameters, they are defined, and then in this sort of circuit calculation, one of the things that we assume is that everything is linear. We are working in the linear region. Okay. When it goes to the saturation region, then this circuit doesn't valid. And then also that you can see that there are losses associated with this circuit as well, like RC, which is the core loss, and then CT resistance loss, and then primary whatever the losses associated with the primary side. And then this circuit is also is important to understand that there is an error associated with the CTs as well, right? If you look at this equivalent circuit, this is the primary current, real primary current, and this is the real secondary current. But the turns ratio, the relationship between is giving the relationship between the primary current and the IP double dash, not IS. So if we say that, if we measure, like let's say, if someone will give you the CT saying that this turns ratio is 100 to 1. And then when there is a 100 amp current is going through the primary, we assume that it has to be 1 amp. But see, with that turns ratio, that 1 amp is actually IP double dash. IS, or the secondary what you measure, could be 0.9 amps because of this excitation branch, right? Now, if you go and then look at the real transformer, you don't have any excitation branch, you can't see it, right? This is an equivalent model. So those current differences happens because of the flux and a lot of other things, right? But then losses and all. But then when you are looking at the equivalent circuit, it's easier for you to understand it. So primary current is here, and then the secondary current is here, which is the current measured by the relay. But the ratio between primary and secondary is not exactly equal to the turns ratio. Because of that, some error is introduced. So we will look at mathematically how we can represent it. You can see that turns ratio is given as NP divided by NS, or the current ratios between IP and IP double dash, see? Right? And then it is defined as, this is just a constant 1 upon Kn. Now once you defined it, there is if you want to calculate the difference between IS and IP, sorry. So we define the error, right? Error as the difference between IP double dash and IS, as shown here. That is the error, right? Error means that IS is what you measured, IP double dash is that what you, if it is correct, that is the measurement. So the difference between them will give you the error. But usually error, simple error is not a best way of expressing the magnitude of error, because let's say if the current magnitude is very small, probably comparable to that current, the error is very, very high. But when the current magnitudes are large, the same error comparable to the current going through the system is small. So that you have two different cases. If you have error, the same error, when the current magnitudes are lower and higher, will give you a sort of a different type of magnitudes relative to the real currents. So the best way to look at it is that percentage, not the absolute error. So that's why the error is divided by the expected current, right? So once you divide it by that current, then the error will be a sort of a ratio of the current going through the system. So that's what they have done. All calculations are done, referred to the secondary side, right? So IS, IP dash and IP double dash, all these current magnitudes are in the second. So you have to do that in secondary side, not in the primary side, okay? So this is called the current error ratio. And then if you look at what I have done here, IP double dash is replaced with IP and KN. Okay, why I don't want IP double dash in my equations? What is the reason? Why I don't need it, IP double dash? Because that is something, unmeasurable. There's no such thing in if you go and then see, if you try to find IP double dash, you can't find it, right? You can see IP and IS, that's all. So then I have to replace this current ratio error with this, right? So this is how you can find the error. And that is the magnitude error, right? We are working with the magnitudes here. But then sometimes there is an angular error as well. So angular error is also important when you are doing the measurements. Because if you are looking at differential current, right? If there is an error, angular error, that will also give you some sort of like let's say if you are looking at two current magnitudes, if they are the same, then they are in the same direction. But if there is an error, then its magnitudes are the same, but slight angle difference. Then that will also give you some sort of a current error, right? So therefore, not only the magnitude, the angle is also quite important. So how do you define the angular difference delta? That is the angle between the secondary vector and then the IP double dash. That is called as the phase displacement error. So when you have these sort of, you can see that here, always these sort of CDs will introduce some sort of a current error, right? Say KNIS minus IP divided by IP, and then which means always KNIS is not equal to IP. To overcome this in a simple way, what they do, they reduce one or two turns, but they still tell you that this is the turns ratio. Actually, the turns ratio, its actual turns ratio is different from what you have seen on the template. In the template, it will say 100 to 1, but actually, they have reduced one or two turns. That you can compensate these sort of errors. So that is the easy way of doing it. And also, it's quite important to look at the, do you need a couple of minutes break? Just to a little bit exercise and we have I think uploaded the marks, right? And I think so. Just double check. But then if you are not happy with that, or if you have any questions, we have a detailed evaluation of what are the issues and all. I would encourage you to go and then drop an email to Kwang. He will send you the detailed information, what went wrong, right? And then also that you can check the answers which I have uploaded. So by comparing that, you can also learn a little bit more. And
So is the second one already uploaded?
which one? Haven't uploaded yet? Ah, okay. So here is. Yesterday night he was asking, is it okay? And I said that yes, please upload. Probably I'll double check. Not yet. Okay. Yeah, assignment is uploaded 4 p.m. Friday. No? Didn't? My goodness. Give me 1 second. It's there. I uploaded it on Friday. You guys should drop me an email. No, I gave you the extension until the Monday. Have to extend it one more day then. What happened? Yeah, it's not. Why is that? Oh yeah, item is hidden. Why is that? See? Should display after this day. Right? That's correct. Probably somewhere here problem. See. Oh no, that's correct. The due date. No. Make the assignment available. Oh. Even on Friday I told that it will be available at 4 p.m. Why it's not available? I think I have to. That's why probably. The other one as well. That's correct. Can you see it now?
Yes.
I will extend the day. That's fine. Until how many days you lost? 2 days, right? I'll put it Wednesday then. Why is that? Extended it until 14, right? Good. Whew. Have to drop an email to everyone. marks are not uploaded, I will say. Okay, done. Okay, we'll come back to the lecture. So the assignment 2 is now available. Sorry for that mistake. And yeah, so there was a setting issue in that one. Okay. Oh yeah, so I will. Thomas is asking the previous week, right, Thomas? Last week one, right? Yeah, that I will make it available today. So just after the lecture, before leaving the room, then I will make it available. Okay? So usually I will make it available Friday stuff on Monday. So when we are looking at the CTs, then it's quite important to look at their characteristics as well, how they change the voltage and what is the relationship between the secondary and primary, right? And for that, here the term IE stands for the excitation current. So if you look at in the previous one, so this is that current, right? That's the magnetization current. So it's like sort of HN, that if you're looking at the transformers, that you can see magnetic flux, and then the horizontal axis that you will see the magnetization current. So that is the same thing, right? So now what happens is that the vertical axis, which is the secondary voltage, is produced by this magnetization current. Okay? And typically it is what our expectation is, that this linear line. This is the line. We assume that for a certain given magnetic excitation current, it will produce a certain voltage, right? There is a linear relationship. That is my expectation. But in reality, they are not. That is how the magnetic circuits work. So therefore, this curve, this black curve, that is basically how it really operates, right? And then it is deviating from this real linear relationship. So by looking at this, then one can look at, or one can define certain parameters associated with these CTs. One of those parameters is called rated. This is very important parameter for identifying the operating region of the CT. So this parameter is called rated knee point EMF. Rated knee point EMF is that if, let's say, at one point of this curve, if the voltage is increased by 10, when the voltage is increased by 10% of its existing value, like let's say now the current value is 100, when it jumps to 110, or to bring it to 110, the amount of excitation current required, right, is 50% more. If it is linear, to increase 10%, how much do you need? 10% of the current. If it is linear, this is 10%, you go 10% in this direction. But you can find, because of these nonlinear properties, at a point where if you want to increase this EK by 10%, you need to increase the excitation current by 50%. So when you reach here, it is 150% of EK. So this one is, sorry, 150% of IEK. that point. And then this point is 110% of EK. Right? So you increased by 10%, the voltage is increased by 10%. To bring that, you need to increase the current by 50%. So when you reach to that point, we call it that voltage as rated knee point. So that's because now you are completely deviating from the linearity. After that point, after rated, which means, right, because when you go work with these sort of real engineering problems, you have to define something very clearly so that the industries can use that information and then everybody is in the same, let's say, same understanding. To do that, let's say, if you tell me that it is nonlinear. What is the definition then? Nonlinear means that it's not linear, but what is the level of nonlinearity? Everyone has to come to an agreement saying that this is the level of nonlinearity that we don't want. So therefore, they come up with an agreement saying that at this point 3, which is the point where you define that, okay, now I came to a level where that you say that it is completely going out of the control, that sort of thing, right? And then remember these current magnitudes in this sort of definition, they are RMS, they are not the peak value. Typically, if you look at these magnetization curves, you usually use the peak value because that is the real value. RMS, there's nothing it's just some sort of quantity that you calculated. But then when they present this, usually they use the RMS quantities. Okay. So based on that, why they defined it, you can understand that by looking at this graph. So we define, first we need to find, okay, why we said that linear, we are assuming linear, but it's going into nonlinear. But if it is going into nonlinear, then it introduces a lot of errors, right? If it is nonlinear, the problem is that it introduces error. So if the error is going into a certain maximum level, which we don't want, right? That is the point that we want to say that now, that's enough. I'm not going to use this CT because the error is too much. For that, we need to look at the variation of the error with the, let's say, excitation current or peak current. In this case, I'm looking at the variation of the current with the primary current. You can see that when I am at the point 2, which is, let's say, slightly going away from this linear curve, right? See, this dotted line is the linear relationship. Number 2 is away from that point, so that I have some sort of an error here. But when I am jumping to number 1 point, that point, these two curves are coinciding. The linear one and then the one which is going through of the real characteristics, right? The solid curve is the real characteristics. And then at this point, the error is sort of 0, right? And then you can see that when you are jumping into E3, again, error, there's a certain amount of error here, right? And then when you are going to number 4, beyond this point, these two curves are going into different directions, right? The linear curve is going up, and then this is more or less flat. So now after this point, you can't control the error. Error is, building up to a very high value, right? So when I am saying error is also defined for this in a way that you are looking at, say, KNIS means that your expected secondary current, right? Or say, based on the secondary current, you multiply it by the turns ratio will give you the expected primary current minus the actual primary current. When these two are equal, then the error is 0. If these two are equal, the error is 0. But then, if they are different, then there will be a certain magnitude for them. But why do we take the square root of it? So that you can make always the error a positive value, right? And then we look at, these are the instantaneous, see, these are the simple value, the simple IS and simple IP, which means they are instantaneous values. So if you have these instantaneous values, then you need to integrate it for 0 to t. And then take the square root of it and then divide by IP will give you the error ratio. If you multiply it by 100, then it is a percentage. So that's how you can find the error. Now, someone could ask me, let's say at this point, this graph, top graph, which is basically RMS based. This graph is RMS based. This is also IP is RMS, right? If IP is RMS, then let's say at point 1, right, when the RMS quantity is here, can there be error? Like let's say these two are, like let's say these two relationships are equal at this point, right? This is the RM, this is based on RMS. But your error calculation is based on what? Instantaneous. Yeah. So when the RMS quantities gives you 0 error, can there be still an error related to this? What do you think? So from the RMS point of view, they are overlapping. But what is the difference between these two? When you are looking at the real curve is not RMS, it's always changing. So when you add these differences, then there will be a small error there. That's why that this EC will never become 0 there, right? It's decreasing, right? You can see that the error at 3 is slightly smaller than even error at 1. Okay? See? The reason is that this is based on RMS, right? When you are looking at the instantaneous, you are looking at variation from this point to this, coming back. Got it? Because you have multiple points, right? So your real curve is like that, right? This is, let's say, RMS is a magnitude here, right? This point, probably error is 0, right? For a given, let's say, RMS given curve, at this point error is 0. But then all the other points that you have a certain error, right? So which means that for a given current magnitude of P, IP, right? For IP RMS, then this is the whole curve. And if IP is lying at this point, still other points of this curve are lying on different points of this curve. So that, which means still there is a small error. Okay, so what I wanted to tell you that EC is not, it's not 0. Can't be 0 because the values are changing always, right? So what you need to understand is that when we change the primary current, the magnitude of error changes in such a way that at 4, error is reaching to a limit which you can't bear more than that. I don't want to use this transformer beyond this. This is a limit for the error, right? So that limit is called as, for instrument, limit primary current. For measuring CTs, the 2 different names. When you are going with the measuring CTs, that limit is given a different name. If you are using a protective CT, that limit has been given a different name. So for a measuring CT, it's called instrument limit primary current. So you are not going beyond that. I don't want to do any measurements, right? That is the instrument limit. But when you are going to the protective CTs, you call it as accuracy limit primary current, right? So that beyond that, the accuracy drops, right? So that is how they define it. The ratio of IPS to the rated primary current IPM is called the instrument security. So if you once you find this, right, IPS is the primary current corresponds to the 0.4. Can you see that? IPS is the current, primary current corresponds to 0.4. 0.4 is the point where you have the accuracy limit level, right? So once you find that IPS, then IPS to the rated primary current, this is the rated point, see? Number 1 is the rated point. Ratio is called instrument security factor for measuring CTs and accuracy limit factor for, so when you, for the protection CT. So when you are looking at, let's say if you take a CT data, okay, so when the supplier is providing, they have to provide that. So when you look at the table, you will see that accuracy, this accuracy limit current, primary current, or accuracy limit factor, ALF, those are given with the product, so that you can do the designs based on that. Okay. Symbols for CTs in a real calculation, there are many different symbols used by. This is the dot convention marking that we used usually, but if you are looking at these different standards, right, they have different symbols depending on the countries. So IEC, they marked it not with the dot, they mark the direction of the current flows. These two currents will have the same phase, that is IEC. And then if you go with the NCO IEEE, which is the US one, they marked it in this way, right? You have this dot, but also IP and IS directions. And then if you have looking at the German standards, they mark it in this way, direction of the current, and then I think, yes, the current direction should be marked in this one as well. IS is not marked here, right? So the different standards. But what you need to understand here is that when you go and work in different countries, you will find it in different ways, but the concept is the same. What you need to show is the direction of the current, right, in the primary and secondary, which shows what is the direction when they are in phase. Okay, let's look at a little bit about the construction as well. Now, the previous things are sort of theoretical and how the calculations can be done and the operation side of it. So usually, depending upon the construction of this primary winding, the CTs can be classified into two different sections, right? Basically, bar type CTs and wound type CTs. Right, so these are the two different type of constructions you will see mainly in the market. So you can see that in the bar type, this is the primary, and then the secondary is wounded along in a sort of a toroid here. But then wound primary ones, both primary and secondary are wounded on the same core, right? So that is the main difference of them. And what else did I miss? Any other information? So out of them, yes, bar types are more common than the wound type in our applications, right? Usually if you look at the normal CTs which I have shown before, they are bar type. But this wound type is, not very common with the power engineering applications. Yeah, bushing or bar type CTs, you can see that these sort of two designs. What you can see here is this is the primary conductor, right? And then when the sort of current is coming in here and then going through this conductor and then going into the other side of the network, right? And then you will have, why do you have two cores? Why do you think? Any reason for having two cores there? Pardon? They are independent as well. Can you see? The two cores are independent. Pardon? Yeah. So one is the improve the sort of security. Like you will have two things now. One fails, the other one works. And the other thing is to compare things, like as an example, what happens if one wire is broken? You need to have some sort of a comparison in the circuit to identify whether there is a local fault or not. Like as an example, suddenly you realize that in one measurement system, or suddenly the current drops or something, and then first thing that you are not going to go and then switch off the circuit breaker. You need to compare it with the other one and then look at, the other one still hasn't changed like that. So the most possible cause of that sort of error is basically a circuit associated with that, so that you don't operate the system, like let's say for unnecessary reasons. Yeah, and then you can see that another bushing type CT here. So you can see that the current is going through vertically through these two, and then still you have those two cores, right? But then there are these sort of different designs, and then in real world, these sort of things. This is called dead tank breaker, because the CTs on these breakers are the ones that measure the currents, right? And then the breaker here, it's an old type of breaker. Usually these sort of breakers, they are used in say, nowadays you can't use those sort of breakers in the suburban areas. They are very, very loud when they operate, right? So that's why that we go for these SF6 and oil breakers and all sort of these things. But then these old types, just for your information here that I put, probably you may not be able to see these things now in future, right? So, but then it's, yeah, from the CT point of view, the important part is that you measure the current on the CTs and then take the appropriate action. Okay, so when you're looking at the CTs, there are two main classes specified by the standards, IEEE, right? Class T and Class C, right? What are the differences between them? We will quickly go through them. The usually they define the accuracy class by a letter, the standards. Like when you are looking at the standards, they will give you a letter to define the accuracy class. And also they will give you the secondary voltage ratings, because that is also important, because that's the insulation. It's not important for our calculations, but it is important reality for the applications in the system. And then that is the primary voltage, but then the secondary voltage is also important, which is given for the operation of our devices, because what we are doing is that we are working with relays. Relays can take certain amount of voltage, so that typically those secondary terminal voltage ratings are also given. So what is the secondary terminal voltage? It is the the secondary terminal voltage means that when you, like let's say for a CT, usually what we are dealing is with current. When you have the rated primary current, you will have the rated secondary current. But then the certain voltage means that when the CT delivered connected to a standard CT burden at 20 times rated secondary current. Can you remember now that 20 time thing? I told you when we select a CT, the fault current, right? When you have the rated current, we multiply it by 20 to see whether the fault current is less than that or higher than that. The reason is this. Okay? So the CT secondary voltage that the CT will deliver when connected to a standard CT burden, right? We will come to what is the standard CT burden. Burden means, what is burden? Burden is the load. Like what is the total impedance across the CT secondary? That is called burden. Because burden is, it's basically if you increase that resistance, it's hard for the CT. So that's why that we call it as a burden. And then this, if you connect a standard CT burden at a 20 times rated secondary current without exceeding 10% ratio error. See? Now what it means, if you, let's say, if you have a standard secondary voltage, so a given secondary voltage, it means that, say, if you connect the standard CT burden at the secondary, if you say that, okay, standard CT burden is 1 ohm, you connect the 1 ohm across it, and then when you send 20 times the rated current, like let's say if the rated secondary current is 1 amp, now I am sending 20 amps through that system. Okay? At the same time, without exceeding 10% ratio error. What does that mean? We are not reaching to that knee point. Because if you reach to knee point, then the error will be more than 10%. Because you are pushing 10% and then you need very high magnetization current. Right? So what they define, what you need to understand here is that they try to define the CT in a way, protective CT, in a way that it can handle 20 times the rated current during a fault condition without a problem. Right? So the system is not going into saturation. Okay. So when I mentioned these two classes, T class indicates that ratio, the class T, you have class T and class C. Class T CTs, their error has to be determined by a test. You can't just define that the overall this old class T CTs have this much of error under these conditions. No way. So you need to do some sort of a specific test, standardized test, to define this curve. See? So to define this curve, you have to do a test by yourself. An example of, like, let's say, example is given here. Why these 1 ohm, 2 ohm, like, 8 ohm, 4 ohm, what does that mean? That is the burden. These are the burdens. Right? That is the impedance connected to the secondary circuit. Can you see now the characteristics changes with the burden? If you increase the resistance in the secondary circuit, the transformer or the CT is going into the saturation region very quickly. But if you have a very low impedance in the secondary circuit, you can maintain the linearity. Right? So that is why that the secondary burden is very important when you are dealing with a CT. With less burden, CT meets linear performance. When the burden increases, the linear performance is not met. Again, you can mention how to find the error associated with this. When you connect different burdens, what is the error? Error is basically primary divided by the number of turns minus size secondary with respect to secondary current, right? So this is basically the magnetization current. IP divided by N minus A is the magnetization current. That divides by the secondary current multiplied by 100 to give you the percentage ratio error. So that is basically, if you look at this curve, right? And then you can find the corresponding error for different points. And also ratio error, which is defined when the CT is not saturated. And then, when the CT is saturated, the coupling between the primary and secondary is reduced. It's not 100% coupled. That's why that you can see that when the magnitude is, the current is certain magnitude, the secondary is not going 100% as before, right? So the magnetic coupling is less. Class C is easier to analyze because it indicates that leakage flux is negligible. The C has little leakage flux, and the leakage, their excitation characteristics can be used directly to determine the performance. And then these excitation characteristics are provided by the supplier, so you have standard C-type curves. And then usually they are more accurate, and therefore their performance can be evaluated using the standard excitation curves, which I will show you in the next slide. So when you are dealing with the real world, if you go into the industry, you will find that the CTs are labeled as shown here, 200 to 5 C100. When you see this, it gives you a lot of information, right? The primary current is 200 amps, the secondary standard current is 5 amps, the class is C, the ratio between the primary and the secondary is 200 to 5, and then the CT will provide linear response up to 20 times the rated secondary current, provided the burden on the secondary is kept below 100 divided by 5 times 20, which is equal to 1 ohm in this case. You got the point? Like, let's say the CT will provide linear response up to 20 times the rated secondary current, which is 20 times 5, right? This 100, and then on the secondary is kept below 1 ohm. How did this 100 means? Can you remember that previously I said that the voltage, 100 voltage is defined in such a way that if you send 20 times the rated current, right, 20 times the rated current, then you need to find the standard burden which limits your secondary voltage at that level. So that is what 100 means. 100 means CT will provide linear response, that is basically low, very low error, up to 20 times the rated secondary current, right? So what is the rated secondary current? In this case, 5. 5 times 20. So that the secondary voltage is kept at 100 for the given burden when the secondary current is 20 times its rated current, right? So when the secondary current is 20 times rated current, which means 5 times 20, which is 100. So to get 100 volts when 100 amps is going through, then you need 1 ohm resistor. That's what it is calculated here. So which means that if you keep a 1 ohm resistor across the secondary, let's say whole impedance in the secondary is 1 ohm, then what happens is that even after 20 times of the fault, like if the fault current is 20 times the full load current, then the CT is working perfectly. Now that's why that we use that 20 thing in the calculations. Okay? These are the typical class C characteristics. You will see it in the lot of from different standards. What it means, you can see that the horizontal axis is IE, which is the excitation current. Vertical axis is the secondary voltage. And then you have different current ratios, from 100 to 5 to 1200 to 5. Right? For different current ratios, you will have different curves. Right? And then this is a small table in the left-hand top corner that gives you, for different turns ratios, what is the secondary resistance of the CT. Because every CT has certain number of windings. Those windings will give you impedance. Therefore, the secondary resistance is also quite important to look at. Got it? So when we do the calculations, we will look at those secondary resistance as well. So we will do some calculations using this graph to identify, what sort of voltage appears in the secondary, what is the error, and all those things we can calculate using this graph. Okay, we'll do it in the calculation sessions. When the CTs are selected, loads connected to the CT, as I said, they are considered as burden. If the burden or the impedance, the relay impedance is very high, error can be very large. The idea of selecting a proper CT is that we want to keep the error in a limited loop, right? So that is what we do in the CT selections. We will do some calculations of CT selections. And then when we are selecting a CT, we need to consider many factors like voltage levels. What is the maximum fault current that, in the circuit? That's what we did in the calculations anyway. We looked at the fault currents, and then the CT ratings, basically the maximum fault current should be less than 20 times the CT rated current. And as I said, voltage ratio, and also that we need to look at if we need to parallel in the CTs. As an example, can you remember the differential protection? The two CTs were connected together, so that if we are not selecting the proper types, then that may lead to errors when the relays are going to connect to those things. This is also very important. see pickup value, right, should be much higher than the magnetization currents. Otherwise, that the magnetization current is the current difference. And then if the pickup value is comparable to the magnetization current, then anyway that you will have that current difference, right? So then that will lead to a sort of wrong operation of the relays. Yeah. So these examples I will cover on Friday. 3 minutes to go through the voltage transformers, right? I'll quickly go through them. It's again the same as CTs, but what you are doing is you are reducing the voltage from primary to secondary. And then the voltage transformers, you will see that in the real life, they are columns, but they are not in the previous, the CTs, there were 2 connections. But in the voltage transformers, you will have only 1 connection like that here on the top. The other end is connected to the ground. So see, this is also depending on the size. Say here it is 420 kV substation. Therefore, you need very longer insulators. That's why it has 2 columns. So it is sort of a VT is very, very similar to the normal power transformer, not like a CT. Because it is just changing the voltage from one level to the other one, and usually the secondary voltages are usually from 100 to 120 volts, because those are the typical voltages used by the relays, right? So that's 100 to 120 is very common. And then the primary voltage can change from up to even 1 megavolt, right? It depends on the transmission system you are working on. And then also the power levels are given in VA, as I said here, represented by VA ratings, right? Capacity or power ratings. That indicates the maximum load which can be connected across the secondary. Not like in the CTs, that in a VT, you need to connect higher impedances, because the secondary is not current driven by the primary current. Secondary is driven by the voltage. So that in the secondary circuit, you want to have less magnitude of currents, which means that you need to have higher impedances across the secondary terminals. This is the typical voltage measurements. And then standard VT ratios, 1 to 2, 2 to 1, like that. And then the bottom column gives you the extension of it from 1 to 1 to 4,500 to 1. Right? So these are the typical ratios that you will find in the standard VTs. Right? So let's say in the primary side, if the voltage is 4,500, then the secondary voltage is 1. So you can reduce the voltage by 4,500 or 4,500 times. There are various different type of VTs. Mainly they are electromagnetic VTs, and then there's something called CVTs, right? CVTs is capacitive voltage transformers, right? So I will go into those 2 different types, and usually what happens is that when the voltage level goes up, you can't just use the inductive VTs. The reason is that you need huge insulation cost is there, as well as you are going up to that's the main thing, like you need to have very, very high insulation there, so that they combine the characteristics of capacitive and capacitance voltage divider and electromagnetic voltage transformer. So I'll go into those things next time, but that's all from me, and we'll see you on Friday. Hello.
So 3.
Pardon?
3 today.
Yeah. Had 1, 2, yeah, 3.
Yeah, let's see. My record.
What is your...
The tutorial. There were also 3, I think. Yeah, there were 3.
Yeah?
For the first part where you explain the differential one, where we have to check the input and output current.
Yeah, yeah.
But for example, if you're checking a generator,
Pardon?
but for example, if you're checking a generator, right? But like generator is at the start of the circuit, then where is the input? Like where do you compare the input?
We generally mean...
Because like in differential, it's like
Yeah.
CT and the protection zone.
No, zone, and then another
and then
CT.
another CT, right?
Yeah.
But when we learn to draw like the line diagram for those grid, it's like generator and then line.
Oh,
so
yeah.
like there's no line behind the generator. Then like how do you compare the?
But you always need to have... oh, you mean... yeah. So this is the generator,
Right. Yeah.
right? And then these are the lines, right?
Right. Yeah.
And then if the generator is grounded like that in send, you put a CT here, CT here, CT here, CT here. And then you can connect them in such a way that you can compare these currents.
Oh, you check where it's.
But
Oh yeah, they will be grounded. No, no.
oh, if it is not grounded, that is also fine. You compare these 3. Right?
Right. Okay.
Total current should be 0, right?
Oh yeah.
Always?
Yeah. So it's 3 phase.
Yeah.
Okay.
Yeah?
Yeah. Okay. Thank you.
So always in between the unit.
Then I have another question, because if you're just checking those 3,
Yeah.
then if it's the fault outside, like
It
outside
won't.
the
It
zone,
can't detect.
wouldn't it still detect, because since the
No.
current
See?
will still change
No.
if the fault is outside?
No. Right?
Yeah.
So now you are measuring the current here, right? See, if the fault is in between these 2, right? Because this is a delta connected system, because we said that this is connected to a generator like that, right?
Yeah.
And then if it is fault between these 2, then these currents will be measured here and here, because current path is this one.
Yeah.
This current is detected, right? This is the load current during a fault,
Right.
right? That current is very small compared to this,
Yeah.
right?
Yes. Yes. Yes.
Right? So then when you compare them, then you compare that it doesn't matter for this one, because you have the fault current here, you have the fault current coming back,
Okay. Okay. I get it.
right?
Yeah.
So
okay.
if it is outside the zone, then always the magnitudes will be the same. Like it's outside the zone, if the fault is there, then still the addition of the CT currents will become 0,
Okay.
right?
Yeah. Okay.
Okay.
Alright. Yeah. Should we do it again? Thank you.
Just started meeting. Where should I log out? Oh,
Yeah,
here.
when they log in.
So not good.
So you give the course all by yourself?
Yeah, this one by myself.
That has a big advantage. If something goes wrong, you know whose fault is it. If you share.
So how many of you share in the? How many of you share a one course usually? 2, 3.
Yeah, last year.
How do you find it? Like I prefer to do it alone sometimes.
Yeah, well, in
That's
that
on my
case,
way.
it's simply because of really 3 kind of different topics.
Yeah.
So it's
Okay.
more numerical,
Yeah.
and then more physical, and then
Yeah.
geophysics is included. So from that point of view, it makes sense. Yeah.
Yeah, so it depends on the sort of type of the course.
Yeah.
If you can divide it smoothly. Good. Oh. First day you were not here, but I was carrying this all the way.
Ah, really? Yeah. But there is no.
No.
Well, then I need to use this. No, okay, yeah. Yeah, because in the past, I remember Good morning, hi. In the past, past is good. I'm sitting at the moment, I'm free of teaching, so I was not teaching for a long time. So I was always carrying this thing around. Had to make sure the batteries are changed.
Yes.
Exchange batteries.
Everything okay?
Yeah, I just log into Zoom here.
Sometimes I think, if you forget your phone one day.
Oh,
you
yeah.
go there.
Yeah, you can't park, you can't park. Yeah. It's edit mode. Wait a minute, where is the damn it.